I appreciate the opportunity to be here. Um, as Tim said, the title of the presentation is New Developments in Lightweight Concrete Masonry and How They Benefit the Mason Contractor, and we will be covering the 4 topics shown on the right-hand side of this slide. The structural aspects of the masonry, lightweight masonry, and how recent changes to codes and standards affect the ability of lightweight concrete block to provide efficient structural designs. Also, we'll be looking at energy aspects of lightweight concrete masonry and how those changes to the codes and standards allow us to provide even better energy savings than before. Now, you may look at those 2 items and say, how do those affect a mason contractor? And I would say maybe they don't affect the contractor directly, but indirectly they have a huge impact because they both play into making concrete masonry more economical and competitive against other wall systems. And if we can be more competitive against other wall systems, then there's going to be more masonry construction, which is good for all of us. Then we'll look at the productivity aspects of lightweight masonry and how those are enhanced by these so-called next generation units. And finally, at the end, we will look at the issue of airborne crystalline silica and regulations for limiting exposure to our employees and how lightweight concrete masonry can help us meet those regulation requirements. I want to thank MCAA for the opportunity to present this webinar. It is presented on behalf of the Expanded Shale, Clay, and Slate Institute. ESCSI is the trade association of rotary kiln structural lightweight aggregate producers. My name is Jeff Speck, and I am currently the ESCSI board chair, but I'm also the general manager for marketing and technical sales for Arcosa Lightweight, which is a member company of ESCSI. So let's get started and take a look at the structural aspects of concrete masonry and lightweight concrete masonry in particular. But before we do that, let's talk a little bit about definitions. What do we mean when we talk about a lightweight concrete masonry unit? ASTM C90 is the standard for load-bearing concrete masonry units, and it divides masonry units into 3 categories based on the density of the concrete in those units. Those categories are 125 pounds per cubic foot and higher. Those are called normal weight in the C90 specification. Units that are between 105 and 115 pounds per cubic foot are called medium weight. And units that have a concrete density below 105 pounds per cubic foot are called lightweight units. And the standard references 2 specifications for aggregates to be used in in concrete masonry units. Those specifications are C331 and C33, which I'll talk about more in a little while. But for the purposes of this presentation, we're going to refine C90's definition a little bit. We're still going to use the definition of less than 105 pounds per cubic foot on the density. I'll show you some information on units with densities as low as 85 pounds per cubic foot, which obviously is less than 105, so that's a lightweight unit. And when it comes to the aggregates, we're going to be talking about lightweight aggregates that are specifically expanded shale, clay, and slate aggregates, which we refer to abbreviated as ESCS, because those aggregates meet 2 ASTM specifications, C330 and C331, and I'll talk more about that. As far as we're concerned, C33 normal weight aggregates may or may not be used depending on the density of the unit that a producer is trying to produce and the density of the lightweight aggregate that's being used to produce those lightweight units. ASTM C90 has provisions for compressive strength and it requires a minimum compressive strength for load-bearing units to be at least 2,000 psi on the net area of the unit. That's up from 1,900 psi on previous earlier versions of ASTM C90, and I'll explain a little bit later about why that change was made from 1,900 to 2,000. But it's important to point out that, virtually no block producer tries to produce units to the minimum requirement of ASTM C90 for reasons of making sure that he's in compliance with project specifications, but also for the ability to get green strength and handle and maneuver those units in the block plant itself, as well as having the units be able to withstand handling out in the field without damage. A more typical minimum strength is really more like 2,500 psi, and so I'm going to use that value as we talk about the structural aspects of lightweight concrete masonry. We can do that because we're talking about units made with ESCS aggregates that are a structural grade aggregate. I'll expound on that more in a few minutes. But expanded shale, clay, and slate, it sounds like three different types of aggregate, but it's really one aggregate type that's referenced in ASTM C330 and C331. And it's a manufactured aggregate, and it's graded to provide the optimum gradation to achieve good compaction in the block machine, high strength, low shrinkage, and a uniformity of texture. Now, just to comment on texture, texture is something that kind of is in the eye of the beholder, and it tends to vary regionally as to what type of texture is acceptable in the marketplace. So ASTM C331 specification for lightweight aggregates for concrete masonry units doesn't have grading requirements. So that gives us the flexibility to produce the grading necessary to provide good uniform texture that's acceptable in the marketplace wherever that manufacturing is taking place. So some of you may not be familiar with what ESCS is, so I like to show this picture because it shows a very good depiction of the difference between lightweight aggregate and ordinary materials. 4 of those cylinders that you see in that picture contain what's usually referred to as normal weight materials, or I like to call ordinary materials: sand, limestone, gravel, and soil on the right-hand end. And the center cylinder contains a composite sample of expanded shale, clay, and slate lightweight aggregate produced across the United States. Each of those cylinders contains 1 pound of material. And if you look at the table that those cylinders are setting on, you'll see some lightweight aggregate particles at the base of that center cylinder because they wouldn't all fit in the cylinder. So you get more than twice the volume for a unit weight of material when you're talking about lightweight aggregate compared to ordinary materials. It is a manufactured material produced in a rotary kiln. It is ceramic, regardless of whether the raw material is shale, clay, or slate. Once it exits the kiln and cools, it's no longer shale, clay, or slate, but it is a ceramic structural aggregate that has less than half the density of ordinary materials, and it complies with both ASTM specifications C331 and C330. There are 3 actually lightweight aggregate specifications in ASTM, and you see those designations there on the slide, and each of them has requirements for these physical properties, from grading and strength to durability and shrinkage and so forth. Expanded shale, clay, and slate, or ESCS aggregates, first and foremost, are produced to comply with ASTM C330. That is the specification for lightweight aggregate for structural concrete. There are aggregates included in ASTM C331 that are not included in C330 because of their inability to produce structural concrete in accordance with the specifications of C330. The next ASTM specification is C331, which is the specification for lightweight aggregates for concrete masonry units. And expanded shale, clay, and slate materials also comply with C331, particularly has an advantage when you're looking at things like staining and pop-outs and shrinkage. We have no problems meeting all the requirements of C331 as well as C330. The third specification is C332, which is lightweight aggregates for insulating concrete. And although expanded shale, clay, and slate is included in the materials covered by C332, we don't really pay much attention to C332 because we're more focused on the structural grade materials for producing structural concrete and concrete masonry units. So if there are no questions at this point, I will proceed and get into the structural discussion, which won't take long. Obviously, dead load is the term for self-load, if you want to call it that. So the weight of the wall is really what produces the dead load, and as you reduce the weight of the units, you reduce the dead load produced by that wall. And that means that the supporting structures for the wall, whether they be beams and columns or foundations, don't have to be quite as hefty as they would if those were normal weight concrete or heavier units. And so there's a material savings in the supporting structures themselves due to the fact that the units weigh less. But we also have an advantage when it comes to lateral loads. Lightweight units utilizing the minimum strength that I mentioned earlier of 2,500 PSI, we can produce taller and thinner walls than we could produce previously under the old provisions of ASTM C90 and the TMS code because of changes that have been made recently in the unit strength method in the code. And I'll talk a little bit more about that in a second. But the fact that we can produce taller and thinner walls means that we can reduce the width of the wall, or the thickness of the wall, if you will. We can space the vertical reinforcing farther apart, which means that there's less reinforcing steel. It means there's less grout in the cells that contain vertical reinforcing steel. And there's also less material in the units themselves because the higher strength allows us to use a thinner wall than we used to be able to use. And so that has advantages as well. I mentioned the unit strength method in TMS 402, and I want to kind of explain that a little bit. When a structural engineer is designing a masonry wall, there are a couple of things he needs to think about. He needs to think about what is the design strength of the wall, usually referred to as F prime sub M. That's the specified compressive strength of masonry that he's going to use in his design. And he also needs to think about the type of mortar that he's going to specify for the wall. And usually he's going to specify type S. He might specify type M if he's got really high vertical loads, but more often than not, structural concrete masonry is going to use type S mortar. And he can go to TMS 402 and look at table 2, and he can say, okay, if I've got type S mortar and I'm specifying a concrete block weight of 2,500 PSI, I can use an F prime sub M between 2,000 and 2,250, and I can interpolate and come up with that number that you saw in the previous slide of 2208. So he could use 2,208 PSI for his net area compressive strength of masonry, and base his design on that and specify a block strength, and that's all that's needed to be able to show conformance with the specification. Now, previously, up until just a few years ago, this table was a lot different. The numbers in this table, 1,900 PSI block strength, used to provide a according to the unit strength method, only 1,500 PSI net area compressive strength of masonry. Some research done by the NCMA showed that there's really a one-to-one relationship between the unit strength on masonry and the prism strength on masonry. So the prism strength being the other way you can verify that you're meeting the net area compressive strength requirement on the masonry wall. So when that one-to-one relationship was established, this 1900 PSI strength unit now produced a 1900 PSI wall strength, but 2000 PSI units also produced a 2000 PSI wall strength. So that's when the change came in ASTM C90 to change the minimum compressive strength on the units from 1900 to 2000 so that we could take advantage of this one-to-one relationship. Above 2000 PSI on the unit strength, the one-to-one relationship kind of goes away. So there's a more conservative factor is used. And so you go from 2000 to 2600 on the unit strength to get from 2000 to 2250 on the net area compressive strength of masonry. But in our case, we're going to suggest 2500 PSI, which produces just a little over 2200 on the specified compressive strength of masonry, which is a huge improvement over what it used to be. It's almost 50% higher design strengths are allowed now using the unit strength method than were used under older versions of the code and standards. So it's a tremendous accomplishment on the part of the industry to get the actual strength of the masonry recognized in the codes. So the upshot is that we're able to build taller and thinner walls, which results in more usable area inside the building for the owner. If the thickness of the walls is less, that leaves more open floor space inside those walls. So the owner has more leasable space or usable space if he owns the building. They also enable the reduction in the amount of materials that are used to construct those walls, which is going to reduce construction costs, making concrete masonry more competitive. And that means if it's more competitive, there's more projects designed with masonry, there's more projects for us to bid, and it's better for the future of the masonry industry as a whole. So that's all I'm going to say about the structural aspects of masonry, and I'm going to ask Tim now to pop up the first poll question that he has as I move on to the next slide. I mentioned next generation units earlier, and now I want to talk about what we mean when we say next generation units. ASTM C90 is let me get rid of this little box on my screen. ASTM C90 is the specification for load-bearing concrete masonry units in ASTM, and it provides minimum requirements for concrete masonry units in both load-bearing and non-load-bearing applications, and it has provisions for minimum compressive strength, absorption, maximum absorption, maximum linear drying shrinkage, and it has dimensional tolerances. And it also has not only tolerances, but also specifies the configuration or the minimum dimensions of different aspects of the units. Now this, in the lower left-hand portion of the picture, is a typical two core, 3 web unit complying with ASTM, the older version of ASTM C90, which had requirements for a minimum web thickness and something called an equivalent web thickness. Now, just to make sure everybody's on the same page, when you're looking at a block, the face shells run the length of the block. There's an outer face shell and an inner face shell, depending on which side of the wall is exterior and which side's interior. And those face shells are connected by what are called webs. These are the portions of the block that connect the face shells and go the width of the block. And the minimum requirement in the old version of C90 varied depending on the size of the unit. For a 3 and 4 inch unit, you had to have a 3/4 inch web. For 6 and 8 inch units, you had to have at least a 1 inch web thickness. That meant every web had to be at least 1 inch thick. And then you had something called the equivalent web thickness, which in the case of an 8 inch block was 2 1/4 inches. That meant the equivalent web thickness of 2 1/4 inches meant that the sum of the web thicknesses on a 3 web unit had to be at least 2.93 inches. Now, if you think about that, if the minimum web thickness is 1 inch and there are 3 of them, you're going to have at least 3 inches. So you're going to comply with the 2 1/4 inch web thickness requirement kind of automatically. In 2011, the requirements of C90 were revised based on a lot of research and testing that was done in the laboratory, a lot of it done by the National Concrete Masonry Association. And as a result of that research, changes were made in C90. Now, the changes that were made don't require any changes on the part of the block producer, so they can still produce the standard 2-core 3-web unit that was depicted in the previous slide, and those units will meet the new version of ASTM C90 just like they met the old version. But it allows changes in the configurations of the block to provide more flexibility for designers to meet energy code requirements, which are getting more stringent by the year. And it also enables us to make units that the contractors can select that are better suited for certain applications, such as walls that have vertical reinforcing steel. We'll talk more about that as we go. So the new requirements changed from a varying requirement on minimum web thickness to a requirement of a single web thickness, of that single requirement being 3/4 inch. And then we no longer have the equivalent web thickness requirement that we had before, but we now have something called a normalized web area. And the requirement for that normalized web area is 6.5 square inches per square foot of face area of the wall. So what does that mean? Well, it means that for every square foot of wall surface, there has to be no less than 6.5 square inches of web connecting the front and back face shells of the units. So that's a big difference. That's a big reduction from the previous requirement. So we no longer have to have 3 webs that are 1 inch thick on an 8 inch unit. Instead, we can have as little as 1 web that's as thin as 3/4 inch and still meet ASTM C90's minimum web area requirements. Now, in the past, under the old versions of ASTM C90, we did have units that were not 3 web units. We had units like these, like the A block that had two webs and an open end, or an H block that had 1 web and 2 open ends. But to meet ASTM C90, those units had pretty thick webs. I mean, the A block typically was greater than 1 3/4 inches, and the H block was typically greater than 2.5 inches in order to meet that requirement that we had for the equivalent web thickness. So what's allowed now is much different, because we can have an open end unit that has 1 or 2 webs that only have 3/4 inch. So that translates into the old requirements produced a 3 web unit with 2 cores, and the web area as a percentage of the face area of the wall was about 21% under the old requirements. Under the new requirements, that percentage can be as small as 4.5%. You see a couple of configurations here in this picture that are 4.5%. Others are a little more than that, up to one shows 13.4. But the allowable web area is now greatly reduced from what it was previously, without sacrificing any structural capacity. These two little diagrams are supposed to depict a 12-inch unit. I know they don't look like a 12-inch unit. They look more like a 8-inch unit, but But the values shown in the pardon me, I just clicked the wrong thing. The values shown are for 12-inch units with these configurations, and you can see that the net area is the same, and the values that a structural engineer looks at in his wall design, such as moment of inertia and radius of gyration and section modulus, are virtually the same for both of these units, even though they look a lot different. So the bottom line is that as a result of the research that was done, we can change drastically the configuration of of load-bearing concrete masonry units and still provide the same structural benefits as traditional units did, without any penalty for the fact that we have fewer webs and thinner webs. This is key. Again, you may say, so what, from the standpoint of a mason contractor, but it really is one of the keys in enabling us to use these next generation units to provide the benefits that we're going to talk about next, without sacrificing the structural capacity of the wall. So I think it's time for the second poll question, if I'm not mistaken. Yes, it is. Okay, so I'll ask Tim to pop up the second poll question as I move on to talk about the energy aspects of lightweight concrete masonry and the next generation units. It's a well-known fact that heat passes slower through lightweight concrete than it does through normal weight concrete. That translates into a lower thermal conductivity, which means that lightweight units have higher R values than normal weight units of the same configuration. And it also means that when the walls are insulated, lightweight units make that insulation more effective, producing a higher R value for the wall system than the same insulation with normal weight units. So there are definite benefits from an energy standpoint to using lightweight concrete masonry as opposed to normal weight concrete masonry. Those benefits are even enhanced to a greater degree when we start talking about the new C90 units, or the next generation units that we began talking about. The National Concrete Masonry Association publishes a thermal catalog that contains the thermal properties of just about every concrete masonry assembly that you can imagine, and the insulation strategies that are available to those. And so you can get a copy of this NCMA thermal catalog online at NCMA's website. NCMA also produces a series of tech notes, and this slide contains a portion of one of those tech notes, tech note 6-202C, which talks about R values of concrete masonry walls. And it demonstrates what I just said, that that as the density of the unit, or the weight of the unit, goes down, the R value of the unit goes up. This column contains R values and U values, for which are reciprocals of each other, in case you didn't know, of walls with empty cores. In other words, uninsulated walls, 6-inch walls and 8-inch walls here. As you go from normal weight up to lightweight, you see that there's a pretty significant, about a 30% increase in R value just in the concrete unit, masonry unit itself. But when you go over here to insulated, and if you look at the foamed in place numbers as an example, as you go from normal weight to lightweight with the same insulation, the R value of the wall system more than doubles. It's true in the 6-inch wall, it's true in the 8-inch wall, and if we included the 12s, it would be in there too. So definite benefits to improving the energy efficiency of the wall by using lower density concrete in a lightweight unit. The reason the heat flows slower through masonry units is a couple of things. One, I mentioned the the lower thermal conductivity of the concrete, but also how does the heat flow through a masonry wall? It flows through the webs. The webs transmit the heat from one side of the wall to the other. Those webs are sometimes referred to as a thermal bridge. And if you lower the thermal conductivity of that bridge, you're going to slow the heat flow through the webs. So lightweight concrete masonry improves the energy performance of the masonry wall because of that reduced heat flow through the webs. A few years ago, Jason Thompson, the Vice President of Engineering at National Concrete Masonry Association, wrote an article for Masonry Edge magazine, and you see the title there, Smaller Webs Equal Higher R Values. And in that, he detailed the advantages of using these next generation units to take advantage of less web area to reduce that thermal bridge and increase the energy performance of the masonry units. There are a number of different systems that are used to insulate concrete masonry walls. Some of those are proprietary and some of those are not, but they all act on the same principle, and that is that reducing the heat flow through that thermal bridge improves the thermal efficiency of the masonry wall. And in Jason's article, he shows that going from an 8-inch lightweight unit of the old C90 configuration with 2 cores and 3 webs to a next generation unit with fewer and thinner webs, you get more than double the R value on a 8-inch block and more than triple the R value in a 12-inch lightweight wall. So just a tremendous difference in the energy efficiency of a next generation unit using lightweight aggregate. And those values or typical values are shown on this slide. Again, that same 12-inch unit that doesn't look like a 12-inch unit. You can see the difference in the weight, 48 pounds versus 22 pounds. Now that's a 12-inch unit, 22 pounds. That's with 85 pound per cubic foot concrete density, and this modified A block produces a very lightweight 12-inch unit. You can see the web area, 14 square inches per square foot as opposed to 35 on the other one. And really the benefits of that are here. More than 3 times the R value of the insulated wall when you have lightweight concrete masonry. So it's tremendous. So again, from a standpoint of a mason contractor, what's in it for me? Well, we're enabling these concrete masonry walls to meet the ever more stringent energy codes that are out there, which is getting harder and harder to do. And we can do it with a single wythe concrete masonry wall. We don't have to do a cavity wall with insulation in the cavity or any extreme measures. We can do a single wythe wall and still meet the energy code, which is, and it's really about the only way a single wythe wall is going to comply. And by doing that, we're going to help keep some of our traditional concrete masonry markets and perhaps expand those markets into areas that we've lost along the way. And if we can increase the amount of concrete masonry in the marketplace, more projects being designed, more projects to bid, more projects to build, that's better for mason contractors, it's better for the block producers, it's better for all of us. So it's important to all of our futures that we produce units that are not only structurally efficient, but also energy efficient. So I think with that, I'm going to ask Tim to pop up poll question number 3. And I'm going to move on to productivity, mason productivity. It's another well-known fact that as the weight of the units that a mason is working with decreases, that mason is able to produce more wall area in a given period of time. This principle is applicable regardless of whether you're talking about concrete masonry or brick and what the configuration of the unit is, the lighter the units, the more units that a mason can get in the wall in a given period of time. And it's not necessarily that he is working faster, he or she, excuse me, but that the mason is able to maintain his or her normal rate of production for a longer period of time without fatigue setting in and slowing them down. So lightweight units increase productivity. A gentleman by the name of Kalkowski wrote a book, Masonry Estimating, a number of years ago. And in that book, he included this graph, which he refers to as the concrete masonry production curve. And he also had a similar graph for brick. And he made the point that we shouldn't get hung up on the specific numbers that are shown here for production for different weight units, nor should we get hung up on the fact that he has two-man block shown at a 37-pound unit. He said that these numbers and all the details in this graph were specific to one specific local market, but that no matter where you are, you can produce a similar graph for your masons in your market, and it will have a similar look to it, showing that as the weight of the units decreases, the productivity potential increases. And so that's the whole point of this slide. Not only does lightweight concrete masonry enable greater production efficiency, but it also reduces the potential for injuries. And lower injury rates result in fewer workers' comp claims, which results in lower insurance rates, which all factor into the profitability of a mason contractor. This was verified by the Center for Construction Research and Training, which said that masons have the highest rate of back injuries among construction workers. And the reasons for those are the weight of the units that they're lifting and the frequency of lifting and twisting and reaching high and stretching out away from themselves as they're lifting these heavy units. The combination of those things are what result in many of the injuries that we see today. So, and one key area that causes problems is lifting heavy units up and over vertical reinforcing steel. If we can eliminate that, we can eliminate not only injuries, but also think about how much that slows a mason down. How does that affect mason productivity? So this is where the next generation units come in. If there's at least one open end in a unit, we no longer have to go up and over that reinforcing steel, but we can go around it. And if we produce those units out of lightweight, we have a significant weight reduction compared to the normal configuration, normal units, up to even greater than 50% reduction in weight when we're talking about 12-inch units. So the blocker lighter, 40 to 50% lighter, which increases productivity well above our normal estimates for productivity and above those published in things like NCMA's Tech Note. And if we take advantage of an A block or an H block with at least one open end, they're easier to maneuver, and we can lay those around vertical reinforcing steel instead of going up and over vertical reinforcing steel. And that's going to help eliminate or reduce drastically the potential for injuries and also improve productivity. So here's a picture of some A block, modified A block in a wall. And I've got an example of a project in North Carolina utilizing a 5-man crew laying 10,000 units using lightweight next generation units. Took a little over 7 days, while using the old configuration units would have taken almost 12 full days. So I'll let you do the math on the savings of being able to complete that amount of work in 4 fewer days. So in summary, when it comes to productivity, lightweight units offer better productivity than normal weight units, and next generation units also offer better productivity potential compared to ordinary old generation units, if you will, units made under the old C90 provisions. But when you combine lightweight and next generation units, it takes production to a whole nother level. So it's really the best of all worlds to utilize these next generation units that are lightweight to get the best possible productivity and reduction in injuries, and all without sacrificing structural performance and actually enhancing thermal performance. So again, the upshot of this is that all three of those together help make you, the mason contractor, more competitive, makes masonry more competitive against other materials, and is better for the future of the masonry industry. I'm going to move right along and get into the issue of airborne crystalline silica. Now, recently, federal regulations went into effect that require employers to make sure that their employees are not exposed to more than a certain amount of airborne crystalline silica. And when it comes to mason contractors and masons out in the field, this really comes into play when we're dry cutting concrete masonry units. If we're wet cutting, it's not an issue, but dry cutting up on a scaffold or somewhere where we don't have access to water, we're going to create dust, and that dust can contain airborne crystalline silica. Because lightweight aggregates contain less silica than normal weight aggregates, blocks made with lightweight aggregates produce less airborne crystalline silica when they're sawed than normal weight units do. Lightweight aggregate has 1/3 the crystalline silica content that granite aggregate has, and it only has 1/8 the crystalline silica content that natural sand has. Natural sand, sometimes referred to as silica sand, so no surprise that it has a very high silica content. So the exposure to the mason really depends on what type of unit is being used to produce, what type of aggregate is being used to produce the units. So the axiom is that the more crystalline silica there is in dust, the less dust may be breathed by the employee. Translated, it means that we have to be able to show that we're not exposing our employees to levels of airborne crystalline silica above the personal exposure limits, and even better if we can limit it to below the action limits that are in the regulations. So I'm going to show you here an example calculation of how we can know how much crystalline silica we're exposing people to. This shows the example of 8 hours worth of sampling of the air, dust collected in the air in that sample of 0.05 milliliters in that 0.816 cubic meters of air. And in that dust, the quantity of airborne crystalline silica in the dust depends on what aggregate is used to manufacture the block. If lightweight aggregate, expanded shale clay and slate lightweight aggregate is used, that same sample will translate into 16.5 micrograms of crystalline silica per cubic meter, which is below the action limit in the regulations. That's a key point right there. If granite aggregate is used to produce those units, the calculation shows 49.6 micrograms of crystalline silica in the dust per cubic meter, which is below the PEL, the personal exposure limit, but it's above the action limit. So it means we have to take actions prescribed by the regulations. And if the block is made with a granite and sand mix, that amount of crystalline silica now jumps up to 160 micrograms per cubic meter, which is above the personal exposure limit. So that means breathing apparatus and all kinds of measures that have to be taken to maintain compliance. So the bottom line is that lightweight units made with expanded shale clay and slate lightweight aggregate are below the action limit in terms of airborne crystalline silica when you're sawing those units, dry sawing those units. So in summary, expanded shale clay and slate lightweight aggregate concrete masonry units have a lower silica content than other masonry units, and therefore limit the exposure of our employees to airborne silica. And with that, I'm going to have Tim pop up poll question number 4. And while he does that, I'm just going to mention decorative lightweight concrete masonry units. I mean, usually when we think of lightweight concrete block, we think of gray block, like this one. Sometimes I call it the old gray mare. But the fact is that lightweight aggregate can be used to produce decorative units as well, particularly the earth tones, like you see here in these pictures, are easily made with lightweight aggregates all year long. And half-high units are very popular now. They produce a very attractive building, as you see here in this example. So we can produce beautiful decorative concrete masonry units out of lightweight aggregate and have the benefit of the lower silica content. So something to keep in mind when you're talking to your local block producer. Now I'm going to summarize. The bottom line is that lightweight concrete masonry, combined with the new shapes permitted by the recent changes in ASTM and changes to the unit strength method in the TMS code, combine to help make masonry more competitive in the marketplace, which means more projects can be designed and built out of concrete masonry. It means more business and more profits for the concrete masonry producer and the mason contractor. Everybody in the industry benefits, and it makes the masonry industry more sustainable, gives it a brighter future, and just good all the way around. So I don't know why anybody would want to do anything else. And with that, I want to thank you for your attention. Here's a summary of what we talked about. And I'm not going to read that slide because everybody can read. But for more information, I would point you to ESCSI's website, escsi.org, for more information on the benefits of lightweight concrete masonry. I would thank you for your time, and I'll open it up to questions.
All right, Jeff, we have a couple questions for you. The first one is, how does lightweight concrete masonry strength compare to heavier units?
Well, the usual answer is that it's exactly the same. It is possible to produce very high strength units with harder aggregates. So if a project requires extremely high compressive strengths for the units, it may not be possible to achieve those with only lightweight aggregates. You might be able to do it with a combination of lightweight and normal weight aggregates. But I would caution you to discuss that with the block producer, and it may be possible to meet those strength requirements with lightweight units, but it's something that would just have to be tested on a case-by-case basis. But in the ordinary, in the typical, I should say, as opposed to ordinary, the typical range of compressive strengths that are specified for concrete masonry projects, lightweight units can produce those just as easily as normal weight units.
Next question is, why aren't we seeing more next generation units specified for our projects?
I would say probably because architects and engineers don't know about them yet. I mean, it's incumbent on us within the masonry industry to get the word out on what's possible. I talk about next generation units every time I do a seminar for engineers and architects, because I want them to be aware of what they can do, what the next generation units can do for them in terms of their design and what they can offer to their clients, the building owners. But right now, I would say the reason you're not seeing more of them specified is because there's just a lack of awareness out there among the design community. So it's going to take a little time for us to make them aware of what's possible.
All right, next question. Can you please show the productivity slide with Pro Block and using lightweight aggregates?
See if I can go back to that. I don't know if they wanted this slide, or I don't think this was the productivity slide. So is this the slide that they were looking for?
I believe so, but if not, please type in a question. Oh, she said all good, thank you. So we're perfect.
Okay. Okay.
All right, and then we have one more question. How does lightweight CMU's lower silica content affect my ability to comply with the new regulations?
I would say that it probably doesn't require you to take no action, but it does provide you with a greater level of comfort that if your project site is inspected and if OSHA comes along and starts sampling the air and testing the air sample for crystalline content, that you're going to be in the clear, because the crystalline content, crystalline silica content in that air sample is going to be below the action limit.